Now, guys, let us quickly look at this flow diagram. Most of us in this question, our challenge is that we are unable to work with a flow diagram. So this is how a flow diagram works. You just look at the arrow, where the arrow starts and where the arrow ends. Okay, where the arrow starts is here, for example. That's where the arrow starts. Where the arrow ends is where you have the arrowhead pointing direction. You know that where it starts, this becomes a reactant. Where it ends, it becomes a product. That's all we're looking. Reactant, product, reactant, products. Then what comes into your mind when you do that? You are working with USA, you are working with SU, and you're working with triple S. That is what you are looking at. Now let's quickly look at reaction A. Reaction A, we are looking at the starting point as a double bond over here. That means this is unsaturated reactant. It's a reactant. It is unsaturated. So if it is an unsaturated reactant to a propane, a saturated product, what is it? Unsaturated reactant, saturated product, the type of reaction is addition. So A is an addition reaction. What did we add to get a propane from a propene? We have added hydrogen. Therefore, hydrogenation is the type of addition reaction. Now, let's look at another arrow that is going away from the center, because then it's easy to just work with that one. Another one is this one. From here, it makes, again, propene a reactant to compound Y, but we are adding what? HCl. That means compound 1 is saturated. This HCl here is also what? An addition. This is also an addition reaction. But what did we add? A halogen and a hydrogen and a halogen. So this is hydrohalogenation. Hydrohalogenation. Right, I hope we are still together. Where is another arrow that is pointing away from the center? Is this one. So we have alkene unsaturated. You can see the only one that is unsaturated reactant. So you already know it's addition. So unsaturated reactant to a saturated product. You can see major product. That means we have followed Markovnikov's rule. Okay, we have put the hydrogen where there are more hydrogens and the OH where there is less hydrogen. So here it will be addition. What did we add? We added water, so the type will be hydration. All right, and then the other one will be this one. This one, HBr. Again, this will be addition. What type of addition? It's hydrogenation. D is hydrogenation also. All right, I hope we are okay. We have exhausted all of them. Then we can look at the ones that are going in the opposite direction. So now we are moving from compound Y, which is saturated, to compound this one, which is now becomes unsaturated. So saturated to unsaturated is elimination. We have eliminated, right? All right, now that we have exhausted all the addition types of reactions, now we are going to look at all the arrows that are facing towards prop 1E, okay, this alkene, which is propene. Now we said that we're going to start with C. C, that means that the arrow starts from compound Y to propene. That makes compound Y a saturated reactant. It makes compound Y a reactant. Okay, that then now this becomes a what? A product. This now becomes a product. Now the reactant is saturated. The product is unsaturated. The type of reaction is elimination, as I said. Then we look at another one. As you can see E over here. E is also the reverse of that. We are moving from saturated alcohol to an unsaturated alkene. So the type of reaction on E is elimination also. Elimination. Good. Then, which other one? D. If you look at D quickly, also, we are moving from a major product, which is compound X, which is a saturated compound, from a saturated to an unsaturated compound, then D will also become elimination because we're moving from a saturated reactant, because that's where the arrow starts, to an unsaturated product because that is the arrow head pointing to that as a product. So this means that D is elimination. What was eliminated is what was added. Okay, whatever that was added is what was eliminated. So because you added HBr, it was hydrohalogenation. That means the type of elimination there will be dehydrohalogenation. All right, guys, I think we have exhausted all the types of elimination reaction. Now we're going to go outside. Okay, so if you look here, let's look at B. B, we are moving from a propane, which is saturated, to compound RY, which is also saturated. So saturated to saturated, the type of reaction is substitution. Okay, right. Then check what is it that was substituted. Then where do we go? We can come here to F. Again, we are moving from a saturated compound X. If you still remember, it is saturated. It's a haloalkane because of the HBr that was added. So from a saturated reactant, because that's where the arrow starts, to where the arrow is pointing as a product, then alcohol is also saturated. So F becomes substitution, also substitution. And then G is the last one. From saturated to another saturated, again, G becomes substitution. We just need to find out what type of substitution reaction it is. All right, guys, this is question 5. Normally in previous question papers, it is the topic rate of reaction. What is it that you need to do when you are practicing this chapter? Do not forget to revise your grade 11 work, okay, where you are looking at the differences between exothermic and endothermic reaction. We know that an exothermic reaction is the reaction where energy is released into the surroundings, while the endothermic reaction is when energy has been absorbed into the surroundings. So also look at definitions such as activation complex as well as activation energy. We know that activation energy is the minimum amount of energy needed to start the reaction, and also know what a heat of reaction is. Go back and look at the graphs of exothermic as well as the endothermic graph. Over here, I've attached 2 of the graphs so that I can remind you how they look like. Now remember here, the energy of the reactants becomes more than the energy of the products when you are dealing with an exothermic reaction graph. And then when you are looking at an endothermic graph, the energy of the reactants is less than the energy of the product. Now what is also very important for you to do is to know how to label this graph. Now remember, that will be your reactants, that will be your product, the products, and then that space over there between the reactants and the highest position, that will be your activation energy, and over here would be your activation complex. Okay, activation complex. Right, and then over there, the differences between the energy of the product and the energy of the reactant, we call it the change in enthalpy, which is also known as the heat of the reaction. The moment you know how to label that, you also need to practice your grade 11 activities based on these graphs. Right, now that we have done the grade 11 revision, the next thing is to look at what definitions, again, in terms of the rate of reaction itself as a chapter. What is it that is expected of you? Remember, you need to be able to define rate of reaction. Remember, the rate of reaction according to our exam guideline is the change in concentration of the reactants or products per unit time. So you need to know how to define the rate of reaction. You also need to be able to state the collusion theory and be able to apply the collusion theory in a question where they're asking you to say, use the collusion theory to explain how the following factor affects the rate of reaction. Now over here, I've indicated the points that are most important, or the points that will always remain the same when you are looking at the factors that are affecting the rate of reaction. We know that when you define the collision theory, the first point will be that the particles must collide in order for a reaction to take place. And in order for the reaction to take place, those particles need to collide with the correct orientation, or they also need to have enough kinetic energy to do what? To react. And then we say that when the reaction is able to take place, then there are effective collisions per unit time. Altogether, that is just the collision theory. So what is it that I want you to know as you are going to be looking at the factors that are affecting the rate of reaction? I want you to memorize these 3 points, because these 3 points will always be the same when you are looking at the other factors that are influencing the rate of reaction. For example, more or less particles will have enough kinetic energy to react. More or less effective collisions will take place per unit time. Why am I saying more or less? It's because it's going to depend on either you are increasing temperature or decreasing temperature. Obviously, when you are increasing temperature, therefore more particles will have enough energy to react. Enough kinetic energy to react, and more particles will have effective collisions per unit time. Now that you have looked at the collision theory, let us look at the factors themselves that are affecting the rate of reaction. And what is it that is different in terms of the collision theory? What is the first statement that is going to be different in all of them? Remember, I said that the 3 bullet points that I've indicated here will be the same for all the factors, but what will be different is the first bullet. Right, now let us look at the factors that are affecting the rate of reaction, and we are also going to look at what is different in terms of the collision theory, that first line that you must know for each and every factor that is affecting the rate of reaction. Remember those 3 points that I spoke to you about in the previous slide, that they must remain the same. Then what is different is the first slide that we are going to be looking, the first bullet that we are going to be looking at for each factor. One, the factor that affects the rate of reaction is either you're increasing or decreasing temperature. If you are increasing temperature, then the average kinetic energy of the particles will also do what? Will increase. If you are decreasing the temperature, then the average kinetic energy of the particles will do what? Will decrease. Then if you are still increasing the temperature, remember those 3 points will also still be the same, meaning more particles will have enough kinetic energy to react and more effective collisions per unit time, and the rate of reaction is going to do what? To increase. So that is what you need to focus on. The 3 points, the last 3 points are the same. The first point is the one that is different. All right. Another factor that is affecting the rate of reaction is surface area. So in terms of the surface area, if you are increasing surface area, therefore more points of contact for collisions between reacting particles are going to occur. Now, more effective collisions per unit time also, and then more particles will have enough kinetic energy to do what? To react. Then the next one is concentration. Remember, is either you are increasing or decreasing concentration. What will be different in terms of the collision theory? There will be more or less particles per unit volume. That is the first line that you need to write. If you are either increasing temperature, therefore you just say more. If you are decreasing, concentration rather, you're going to say more. Or if you are increasing concentration, you will say more. If you are decreasing it, you are going to say less. All right. And then the other factor that is affecting the rate of reaction is adding a catalyst. Now, adding a catalyst provides a path of lower activation energy, and then more effective collisions per unit time, and more particles will have enough energy to do what? To react, or they will have enough kinetic energy rather to react. And then the last factor is the nature of the reactant. So in terms of the nature of the reactant here, we are looking at whether the substance is a solid, a liquid, or a gas, and we are also looking at the physical appearance and the state of that particular substance, and then it is the one that is going to tell us if the rate of the reaction is going to increase or decrease. Now that you know the factors that are affecting the rate of reaction, very much important to know them. Remember, it's 5 of them. It's temperature, it's concentration, it's adding a catalyst, it's the nature of reactant, as well as the adding of a catalyst. Now that you know the factors that are affecting the rate of reaction, I quickly want us to look at the graph. You must familiarize yourself with this graph, the Maxwell-Boltzmann distribution curve. Very much important to know what each label means in the graph, because the examiner can give you a graph where you are looking at temperature versus time, or concentration versus time, or catalyst versus time, but you are given in terms of the Boltzmann distribution curve. So you need to understand what the graph itself, what it means. Right, on the y-axis you can see I have the number of particles, and on the x-axis I have my kinetic energy. You can see all the space that I have over here. You can see that my graph is going all the way up, and then it curves and then comes down, and then eventually comes to an end there. So what is it that you're going to focus on? You need to know what is this open space for. It represents the number of particles represented by this area. It represents the number of particles rather that do not have enough kinetic energy to do what? To react. All right. And then at this point, you see, the moment you see this line over here, that represents the activation energy. And then just at the start of this activation energy, that is where you start having the particles that have enough energy to do what? To react. And then over the shaded area over here, this is the number of particles that have enough and more sufficient energy to do what? To react. So at this point and beyond, which is where the activation energy is, it's where the number of particles that have enough kinetic energy to react actually do what? Actually start. The moment you understand this graph, then you'll be able to understand when you are looking at temperature versus time, concentration versus time, using the same concept of the Maxwell-Boltzmann distribution curve. Very much important to go back to revise it. Now, let me give you tips that you need to take into consideration as you are doing your rate of reaction, the problem solving strategy. Point number one, I want you to read the question with the aim to understand it. Don't just read through for the sake of reading. Let us read to understand and interpret the statement. The next thing that I want you to do is to identify which factor is being investigated. Are they talking about temperature? Are they talking about concentration? Are they adding a catalyst? Are they talking about the nature of the reactant? Are they talking about the surface area? So you need to be able to familiarize yourself with the factors and be able to identify them when you are given a question. Number three, I want you to refer to the collision theory to explain the factor, which is something that we already did. I showed you that the three bullets are the same. Which three bullets? More effective collision per unit time, more particles are going to have enough kinetic energy to react, and the rate of reaction increases. Remember, you only use more if you are increasing. You use less if you are decreasing. What is going to be different is that first bullet that we looked at when we were looking at the previous slide. All right. Now, what is it that I want you to also know? You need to be able to calculate the average rate of the reactants or the product. Now, when we come to this one, please listen very attentively, because number one, there isn't any mark for the formula of rate, because rate is broad. The examiner can give you rate in terms of the number of moles versus time, or they can give you in terms of the mass versus time, or the concentration versus time. So there isn't really a stable formula where we can say we are awarding marks for the rate of reaction. But what I want to emphasize is that when you are calculating, you can be given to calculate the rate in terms of moles per second. In terms of mole per second, you know that means you're looking at the change in number of moles over what? Over change in time. And then you can also be given in terms of change in concentration over change in time, and the SI units will be mole per decimeter cubed per second. Okay, the other one, the third one I want to add here is you can be asked to calculate a rate in terms of the mass. So it will be the change in the mass of the object over what? Over change in time. Remember, this one would be then the SI unit will be grams per second, because remember, in chemistry, our mass is measured in what? in grams. All right. Now, another thing that is very important is to take note, if you are calculating a rate of the reactant, remember to include the negative sign in front of your formula, because as you calculate the rate of reaction for the reactants, you will get a negative answer if you are not going to put that negative in front of the formula. All right. But remember, rate is always positive when you calculate it. So all the time when you calculate the rate of the reactant, please do not forget to include the negative sign, because if you don't include the negative sign, you're going to calculate a negative rate, and rate cannot be negative because it is not a vector quantity. All right. That negative, it just indicates that the reactants will be used up for products to be formed. So we don't want to end up with a negative rate answer or calculation. Now, when you are calculating the rate for the product, therefore, there is no need for you to include the negative sign, because remember that the products are formed as the reactants are used up. So you are automatically going to get a positive answer. All right. Very much important to take note of that. The next thing that I want you to be able to do for these tips, you need to be able to do stoichiometry calculations. You know, this rate of reaction is a very broad chapter. So it takes you back to stoichiometry calculations that you did in grade 10, that you also did in grade 11, right? What is it that I want you to do? I want you to practice basic stoichiometry calculations, such as calculating empirical formula and the molecular formula of a given compound. You also need to be able to calculate the percentage yield. Just to remind you of the formula for the percentage yield, let me write it over here. Remember, percentage yield, the formula for that is equals to the actual yield, okay, the actual yield minus the theoretical yield. Okay, we are going to multiply this by 100 because we are looking for a percentage. And then when you calculate your percentage yield and you get the answer that is more than 100%, then you know that there is something wrong with your calculation. Another one that I want you to look at is how to calculate the percentage purity, just to also give you a formula. Percentage purity, remember, why am I giving you these formulas? You're not going to get them on your data sheet. So these are the formulas that you actually need to memorize. So percentage purity will be equals to the mass of the pure substance. Okay. We are actually looking at the relationship between a pure and an impure substance. So the mass of the pure over the mass of the impure sample. Okay. The impure sample. Again, because you are looking for percentage, you are going to multiply it by 100. And make sure that when you get your answer, it is not going to be above 100%, right? Another thing that I want you to look at is the percentage composition. Remember, percentage composition, you want to know how much percentage of a certain substance is inside that particular compound, all right? Very much important. All these are grade 10. Please make time as you are preparing to go back to look at that. Another thing that I want us to be able to do, you look at the graphs. We are going to look at the differences between the temperature, concentration, and adding of the catalyst graph. So these are the only 3 graphs that you need to familiarize yourself with, together with the main graph of the Maxwell distribution curve. These are the ones that I want you to look at. All right, that is the tips that I want you to know. Now, without wasting time, let us quickly look at the graphs that I promised to look at. The graph on the left hand side, it is the temperature. It is a temperature versus time graph. This is a temperature, versus EK, not time, versus kinetic energy graph. Now, how do I know that this is a temperature graph? Is that when you increase the temperature in the graph, you will realize something. Let me quickly go back. Excuse me about that one. You'll see that the 2 graphs are crossing each other. You see here, the 2 graphs are crossing each other. Where they are crossing each other, they are forming a T. So that is the tip for you to see that this is the temperature versus time graph. The moment you see the graphs crossing each other, they are making a T for temperature. Now you'll see here you are given T1 and T2, and the examiner will always ask you which one between T1 and T2 represents a higher temperature. Now a higher temperature, what are we looking for? Remember, this is the Maxwell distribution curve. What is this EA? That is my activation energy. What do I know about all the spaces above after the activation energy, I know that this is supposed to be that shaded area that indicates the number of particles that have enough kinetic energy to do what? To react. Now, if you compare the first graph, you can see that that is the maximum where it can be, and then you can see the second graph, the maximum is there. You can see that this one has less particles, this one has more particles. So the one that shows more, a higher temperature, it is going to be T2. Why is T2 the highest temperature? Because it shows more particles that have enough kinetic energy to react. Remember, increasing temperature increases the average kinetic energy of the particles, and more particles will have more kinetic energy, all right, to react. Take note of that, all right? Anything that is above the shaded area, we are looking at the number of particles that have enough energy to do what? To react. We are not interested in the highest peak here. Remember, anything that is below the activation energy, those are the particles that do not have enough kinetic energy to do what? To react. Now, on the far right hand side, I have a concentration. This is a concentration versus EK graph. Okay, how do I know that this is a concentration graph? Again, I know that because the peaks, I have two graphs. First of all, I have two graphs, and my graphs do not touch or cross each other. All right, that is one clue for you to be able to separate between the concentration versus time graph. The concentration versus EK, as well as the temperature versus EK graph. Now, you will see here you have graph A and graph B. Remember, what is it that you are looking at? You are looking at the point after EK, okay? What is happening? This one has the number of particles. The highest number of particles is there. This one, it shows the number of highest particles is there. So which one shows a higher concentration? The one that shows a higher concentration is the one that will have more particles that have enough kinetic energy to do what? To react. And at this point, that will be our graph what? A. Graph A will show a higher concentration, while graph B will show a lower concentration. Very much important. EA represents the activation energy, which is the minimum amount of energy needed in order for the reaction to do what? To take place. I hope you guys are able to see the differences, and this tip is going to assist you as you prepare for your final examination. The next one that I want us to look at is the adding of a catalyst. Both of these graphs are catalyst graph. Catalyst. So they are all catalyst graph. The difference is that the one on the left hand side, I'm going to call it A, and this one I'm just going to call it B. The one on the left hand side is being represented, the catalyst is represented on the Maxwell-Boltzmann distribution curve. All right. Remember, we know how to interpret it. Now, what is it that we are looking for? We are looking for the EA, but wait a minute. I have two activation energies. I have an activation energy here. I will call it A1, and then this one is A2. So these activation energies, what do they tell me? Okay, you can see that as you go here, if I were to put numbers here, 1, 2, 3, 4, 5, 6, you'll see that as you go to the right hand side, the number of particles that have enough kinetic energy are increasing. Okay, as you go to the left hand side, the number is doing what? Is decreasing. Actually, also the activation energy becomes lesser as you go to the left hand side, and the activation energy becomes more as you go to the right hand side. Now, what is the catalyst? What does it do? Remember, it lowers the activation energy and creates an alternative path road for activation energy to pass through, or for a reaction to take place. Now, which one between this one and this one that I have A1 and A2, between these two, which one shows a catalyzed route? The one that shows a catalyzed route will be the first one, because that's indicated that the activation energy has done what? Has been reduced. Activation energy after the catalyst is going to be A1, because activation energy the catalyst rather, it lowers the activation energy. So EA1 is the one that shows a lower activation energy as compared to EA2. So in this case, you'll know that, oh, okay, when I have a catalyst graph, I will have two activation energies. And the one with a lower activation energy is the catalyzed route. That shows that I have added a catalyst. And then activation energy before the catalyst, you will see it is the one that will have the highest activation energy. The other things, you are familiar with them, the number of particles that have enough kinetic energy, all the shaded area represents that. All right. Or the examiner can give you, rather, instead of giving you the Maxwell distribution curve, they can give you an exothermic reaction or an endothermic reaction. Then what is it that you're going to be looking for? These dotted lines over here, they are representing for you what we call the catalyst. This is a catalyzed route. Catalyzed route. So that will be the catalyzed route. How do I know that? Because a catalyzed route has a lower activation energy, because the job of a catalyst is to lower the activation energy. So the moment you see this one, you know that, oh, wherever there is a lesser activation energy, that means that that is the catalyzed route. That means that I have added a catalyst. I hope you guys can see the difference between the two graphs, which are both for catalyst, that represent adding a catalyst in a reaction. Remember, a catalyst does not form part of the reactants or products. All right. Very much important to remember that. Now, with that information in mind, let us quickly try to do this one. I'm just quickly going to give you 2 minutes to try to attempt this question. All right. Right, guys, now that we have looked at this question together, let us try to see if we can answer it. The Maxwell-Boltzmann distribution curves A and B represent the number of particles against the kinetic energy of the reaction at two different temperatures. Right, you can see already they are telling you that this is a temperature graph. If they didn't tell you that this was a temperature graph, what is it that you were going to look for? You are going to look for two graphs that are doing what? That are crossing each other. Wherever they are crossing, you know that they form a T for temperature. Right. Let's see what is it that they want us to know or to ask, or what is it that they're asking us. 11.3.1 says, what does the line P represent? Right. The line P represents activation energy. You still remember? Very good, guys. It's activation energy. Remember, the minimum amount of energy required for the reaction to take place. Then let's look at the second question. Which curve, A or B, was obtained at a higher temperature? If you were listening very well, we said that the one with the lower peak. Why is it the one with the higher temperature? Because it has more particles. If we compare here, it has more particles that have enough kinetic energy to do what? To react. Therefore, it means that that is an indication that B has what? A higher temperature. So the correct answer there will be B. Right. Then we have 11.3.3 says, explain in terms of the collusion theory how an increase in temperature influences the rate of reaction. Remember, you already have your 3 points that are the same. You are not going to get 0 out of 4. Okay, you already know, you have written down more effective collusions per unit time. You have written more particles have enough kinetic energy to react, and you have written the rate of reaction is going to increase. So you are interested in the first point. Remember, increasing temperature increases the average kinetic energy of the reaction. There it is. At a higher temperature, the average kinetic energy of the particles will do what? Will increase. More particles have enough kinetic energy to react, and then more effective collisions per unit time, and the rate of reaction is going to do what? To increase. And that is how you are going to get your 4 marks. Now, assuming that you did not know the first part, you forgot the first part of the collusion theory, then you are still going to get 3 out of what? Out of 4. You are not going to get what? 0. I hope you can see how this tip is going to assist you as you prepare for your final examination. Guys, we are now done with the rate of reaction, but before I can just quickly let me just quickly go back to the rate of reaction. There's something that I just quickly remembered that is not part of the slides here. I want you to be able to know the differences between the dependent. The examiner can ask you the dependent and the independent variable, because this type of question can also be an investigative type of question. If they ask you for a dependent variable, you know that the reaction rate is the dependent variable, because the rate of reaction, the reaction rate will be the dependent variable. Why? Because the rate of reaction depends on the factor, if the factor is being increased or decreased. So your independent variable will be the factor that you are investigating. Either you are increasing the temperature, increasing temperature will be your dependent variable, or increasing concentration. You see, concentration would be your dependent variable. Adding a catalyst, I'm not going to write all of them. Adding a catalyst, all the factors, adding a catalyst, surface area, so that those are the things that you are going to be looking at. Another thing that I want you to look at is writing an investigative question. Investigative question. When you write an investigative question, the examiner can say, give you an experiment type of question, because it's normally experiment types of question, this question. They can say to you, write down an investigative question. Please, when you write down the question, it must not just be any question. Your question must include both the dependent and the independent variable, right? For example, what can you name as a question here? You can say, what is the relationship between the rate of reaction and temperature? And then don't forget to put an exclamation mark at the end, or question mark rather, at the end of the question. So that is it that you need to know. Remember that it can be an experiment type of question. They can ask you about the dependent and independent variable. When they say to you, write the investigative question, that is what I want you to do. Be able to do what? To write, what is the relationship? Just start with, what is the relationship between the dependent and the independent variable. All right. I hope this tip is going to assist you as you prepare for your final exam. Now, quickly, let us jump on to question 6, which is our chemical equilibrium. What is it that we must remember when we are dealing with this question? Firstly, you need to be able to define the following terms: an open and a closed system. Remember, an open system has a continuous interaction with the environment, while when we look at the closed system, we're actually looking at a system that is isolated, is in an isolated place. And then a reversible reaction, we know that it shows that the reactant can react to form the product, and the product can still react again to form the reactants. And then another definition that you need to look at is chemical equilibrium. We know this one, the dynamic equilibrium, at which the rate of the forward reaction is equal to the rate of the reverse reaction. Very much important to make sure your definitions are according to the 2021 exam guideline. The other thing that I want you to remember are the factors that are affecting chemical equilibrium. Remember, please do not forget the factors of the rate of the reaction and confuse them with the factors of chemical equilibrium. In rate of reaction, there are 5 factors, but in chemical equilibrium, there are only 3 factors that are affecting chemical equilibrium, which is pressure. In terms of pressure, we are only looking at the pressure of the gases, and then we are looking at concentration as well as temperature. Again, it's either you are increasing or decreasing temperature, increasing or decreasing concentration, and increasing or decreasing what? The pressure. Very much important to remember that, right? Another thing that I want you to do is to know how to state the Le Chatelier's principle. Remember, under the rate of reaction, we are talking about the collision theory. However, under the chemical equilibrium, we are looking at Le Chatelier's principle. You need to be able to state it. Remember, it says that when an equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So you need to be able to define it, and you also need to be able to apply the principle when you are given the statement. You need to explain how. Use Le Chatelier's principle to explain how pressure is going to affect chemical equilibrium. So we are going to look at that in more detail to help you remember what is it that you need to look at when you are applying Le Chatelier's principle. Another thing that I want us to look at is to list the factors that influence the value of the equilibrium constant. I don't even have to say factors, because there's only one factor that affects the Kc, our Kc, which is our equilibrium constant. Only one factor over here, which is what? Which is temperature. Temperature is the only factor that affects what? Our equilibrium constant. How does it do that? We will look at that shortly. Right. Now, what is it that you need to remember again about Kc, our equilibrium constant? Remember how to write the correct expression. Okay? Remember, how do you write the Kc? You are going to say, you're going to take the concentration of the product over the concentration of the reactant. Please, this is not a formula. It's not a formula for you to start with. It's not a formula. It's just an expression to assist you to say, when you are writing the Kc, you are going to use the concentration of the product over the concentration of the reactant. So when they require you to write the Kc expression, do not start by writing Kc is equals to the concentration of the product over the concentration of the reactants. You are going to lose the marks. You must write the actual product that you are given from the formula and the actual reactants that you are given from the formula. Another thing that I want you to remember when you are writing the Kc expression, remember we are only writing the Kc expression for our gases, as well as our solutions. Okay, our aqueous solutions. That is the only phases that we are representing on the Kc expression. All right. Remember, liquids as well and solids we do not represent them. Okay, present them. Why are we not representing them? Because remember, they have a concentration that is constant. So because they have a constant concentration, we don't really have to include them on the Kc expression. Another thing that I want you to look at or to remember when we are doing Kc, the Kc value will tell you a lot. You will see the significance of the Kc. I'll talk to it when we talk about that. The next thing that I want you to look at is how to do the calculations. You know, there are so many calculations of the Kc, and most of us, we don't even attempt them. Or when we attempt them, you know, we don't get to the finish line. So hopefully by the end of this lesson, you'll be able to remember how to do the calculation. So perform calculation based on Kc values. Okay, I use the RICE method to help me remember the table that I use when I'm doing my calculation for the Kc. I will explain to you the RICE method when we look at the calculation. Right. The next thing that you need to be able to do is to explain the significance of a high and low Kc values of the equilibrium. Okay, higher or lower Kc values, what do they mean? The first thing that you need to know is that if Kc is less than 1, okay, that means that the concentration of your product, or rather you have more product, it actually means that you have more reactants, rather. You have more reactants than products, okay? And this is not good for you, for a business, all right? Because you want to be in a situation where you are buying less products, less reactants, or any reaction, anything that's going to help you to start the reaction. You must buy it less. And then for the products must be more so that you can make more profit, okay? So very much important. So a Kc that is less than 1 actually means that you have more reactants than the product. And remember the relationship between Kc and temperature, that also means that the temperature has done what? Has decreased. Remember we said temperature plays a very important role with Kc. Decreasing temperature decreases the Kc value. Decreasing the Kc value means that you have more reactants than the product. This is not good for your business. But if you increase the temperature during the Kc, then that means you will have a Kc that is going to be greater than 1, which means that you are going to have less reactant than product. Okay, product, meaning you are going to form more products, which is what you want because you want to make more profit. All right, very much important for you to take note of that as you are looking at the chemical equilibrium. Right, guys, now let us take a break. When we come back, I want us to look at this equation, this question, and then we will be able to do it together. Right.